Good afternoon, everyone. I'm Conrad Denmark. I'm the design team lead for BYOBR, or Bring Your Onboard Recorder. And today we'll be giving you our preliminary design review. So I just want to start off and thank everyone for being here. I know for some of you it's been a long day, and we really appreciate your time and feedback. BYOBR has put a lot of time and effort in this project. We're really excited to share with you guys what we've come up with. So our objective for this presentation, I'll kind of do a quick overview of our program plan and also our team organization, who the team leads are, and their impact on the project. We'll be going over some project requirements. Austin will be going over our concept of operations, and he'll briefly touch on that we have two designs right now we're iterating. So our EE team will be talking about our onboard recorder. As Professor Zwick mentioned, that this is kind of a two capstone put into one. So we're primarily designing the projectile, the 40mm projectile, which we'll cover more of. And then a later capstone team will dwell deeper into the development of the onboard recorder. So we'll talk about our design approach as well, kind of where we started with our initial research and how we iterated down to the designs we have right now. One of the main factors of that was wind tunnel testing. As you can see from our models, our aero team will go more into that as well. We'll talk about structural integration, and interfacing the material we've selected that we'd like to pursue to use, and also proving that it's safe. We'll be able to stand up to the structural loads. And then we'll also kind of talk about the next steps, what we're looking forward to doing next semester and the following semester. So program organization, as I already stated, my name is Conrad, the design team lead. Daniel Green is the assistant team lead. For aerodynamics, Corey Bullens and Austin Fisher. Structures team lead is Rachel Monsterio, and with her is Troy Johnson. Walker Dema is our performance lead in stability and controls. Cole Burkett is our electronics team lead, along with Yuhan Godfrey Sung and Marshall Thompson. And Will Smith is our systems lead. So our program plan. We started off with some requirements built by Professor Zwick and Raytheon, asking us to build a 40mm projectile that houses an onboard recorder. The main thing about this recorder is that it's supposed to be universal, and it will be. The idea is we can take this recorder and put it into a projectile as small as a 40mm projectile, as you can see here, and use it in various munition systems. So we started our research. We came to two initial ideas of using a straight body projectile and a mortar body. Now one of the big complications we faced was a lot of the data for straight body projectiles is very easily accessible. However, mortar bodies, a lot of that is very classified, and we weren't able to get our hands on that. So that led us to having to do our own research. So we took a bit of a turn and diverted our attention to wind tunnel testing. We created these models, got some time in the wind tunnel, and that took a lot longer than we expected. Complications with spring brake, the RFP lab, making sure that everything was tolerant so it could fit. We kind of had to skip forward to detail almost a little bit and learn about that, and then jump back to iterating designing. And now, with our wind tunnel testing, we're able to use that data to iterate on our designs, and we'll further do that next semester. So I'm going to hand it over to Daniel Green, and he's going to talk about our business case.
Thank you, Conrad. So, why do we need this project? The OBR will collect dynamic flight data such as launch conditions, trajectories, flight conditions, and then using all of that information, we'll be able to model the flight path of the projectile and determine whether or not we hit our target and how far off we were. The projectile itself will allow for a repeatable testing platform for the OBR and protection for it from the loads of launching and landing. So the whole system as a whole will allow us a way to characterize launch data as well as flight information. And the OBR, as Conrad touched on earlier, since it's a small 40mm projectile that it needs to fit into, you'll be able to take it out of that and put it in a larger projectile that you might need it for. So on the whole, this is a very cost-effective program. The system, we're aiming for about 1/10 of the cost of a normal guided munition, so about $7,000, which makes it very cost-effective. Now I'm going to pass it off to Will Smith to talk about the system requirements.
Thanks, Daniel. So before I get into the requirements specifically, I want to define our system for you. So our system, as we're talking about it, consists of the projectile and the onboard recorder, the launcher, computer for data transfer. None of that is included in our system because it's kind of outside the scope of our project. So I'll start off with some performance requirements. Our system has to be capable of withstanding a 1000 G acceleration in the longitudinal direction and a 200 G acceleration in the lateral direction. It also has to be capable of being relaunched 30 minutes after it impacts the ground. As far as physical requirements, our projectile obviously has to carry the onboard recorder through all phases of flight. So that's launch, the actual flight, and impact as well. Our system won't exceed 5 pounds. So we've allotted 4 pounds for the projectile itself and 1 pound for the onboard recorder. It won't exceed 40 millimeters. That's 1.57 inches in diameter, roughly. The 40 millimeter is really where we started because that's about as small as a modern munition will get. And then from that maximum dimension, we derived that our onboard recorder will fit within a cylinder that has a diameter of 0.625 inches and a length of 3 inches. As far as environmental and monetary requirements, all system components have to be capable of operating at 50,000 feet. That's sort of a typical altitude that most munitions will not exceed. And from there, we've determined a very standard temperature range, -40 to 160 degrees Fahrenheit. As Daniel stated, the entire cost of our system won't exceed $7,000. Of that, $2,500 is for the projectile, and $4,500 is for the onboard recorder. I have a quick summary for you to reference in the future. And then I'll pass it over to Austin to talk about our concept of operations.
Thank you, Will. Good afternoon, everyone. My name is Austin, and I'll be going over our concept of operations for our current projectile designs. All right, so currently we are working on 2 designs that we have in our iteration process. One is a non-deployable fin setup, and one is a deployable fin setup. So the aerodynamic objectives of this design for the projectile was to design for maximum range. And so that's why we have the deployable fins set up on the right side over here. So the idea for the deployable fins with those high aspect ratio wings, that allows us, that gives us improved lift, decreased drag, and overall greatest range. However, there is moving components in this design, which is why we also have our non-deployable fin design. So with the non-deployable fins, the biggest reason we did this was because of this bolded part right here, which is the static CG location. So with our in-flight recorder, we want that placed in the projectile at the CG location, the center of gravity. And so with the non-deployable fin design, that center of gravity will not be changing, it will not be moving. Whereas our deployable fin design, that center of gravity will shift as those fins deploy. So this is why we're iterating these 2 designs currently. Here's the concept of operations for our non-deployable fin design. What we haven't talked about yet, and I'm not sure if all of you are familiar with this, but our launch mechanism has what's called the sabot. So this sabot is going to encapsulate our projectile. We have a 40 millimeter projectile, and our launching mechanism, the inner diameter of that launching mechanism is about 52 millimeters. So there's space that we need to make up for to account for. And so we're going to have that sabot make up for the rest of the space outside of the projectile to the inner diameter of the launching mechanism. Once that shoots out of the cannon, it's going to follow its trajectory and hit the ground, in which we're going to dispatch a team to recover our projectile. They'll bring it back, in which they'll offload all the data from the recorder via USB to a computer, and then we'll be able to repeat this design or repeat this process within 30 minutes. So the concept of operations for our deployable fin design is a lot like the first one, however, with the addition of the fins deploying as the sabot detaches from the projectile. And I'll talk a little bit about our onboard recorder and the specifics of the design of that. Is Cole Burkett, Marshall Thompson, and Godfrey Son.
So I'll be going over the OBR requirements. that will eventually get passed on to the next prelim and the detail teams. So first, the data rate. Our data rate is going to be 200 hertz for 1 minute. We want to be able to record at least 1 minute of flight data at 200 hertz so that we can get the flight data that is in their system requirements that we need. And then for our data collection, we're going to apply power to the OBR with an acceleration of 10 Gs detected. And the reason why we're doing this is because we do not want to put the onboard recorder in the projectile and then have it sit there, say, for an hour or so and record a bunch of unused data that we don't need. So once it detects an acceleration of 10 Gs, we're going to go ahead and start recording data then. And the data type that we're going to get, we're going to do body axis accelerations and rates and orthogonal axis angular rates. And this is just basic flight data, and that's why we're building the OBRs to get that data. And like Will stated earlier, we're going to have an operating altitude of 50,000 feet and an operating temperature range of -40 degrees to 160 degrees Fahrenheit. And then the weight of this, as stated earlier, is going to be less than 1 pound, and the size is going to be less than 0.65 inches in diameter, less than 3 inches in length. The reason why we have the size requirement is because we're trying to get a good slenderness ratio of the projectile itself, so therefore we're keeping it within these constraints. And then also for the cost, it's going to be less than $4,500. The reason why we have more money towards the OBRs for the electronics and other electrical equipment that's generally more expensive than just building the projectile. And the next, actually Godfrey is going to talk about the block diagram.
So the block diagram, the OBR is powered by a lithium polymer battery, which is then, the voltage from it is then filtered and smoothed from a capacitor. The filtered voltage is then put into a breakout board, which integrates all the key components of the OBR together. The IMUs, the internal measurement unit, consists of a triaxial gyroscope, a triaxial magnetometer, and a triaxial accelerometer. The IMU will yield the roll, pitch, and yaw angular rates, and these rates will then be filtered out through the MAF, EKF, and FIR into a data acquisition module, which in this case would be a micro SD card. And the GNSS would be used for locating the projectile once it needs to be collected. And for any additional questions, refer to the block diagram description. Now, Marshall Thompson.
Okay, with every key point that Godfrey has hit on, we have a power consumption chart for those IMUs and our components. Each of these parts were acquired data sheets, and on those data sheets you have required voltage and operating currents and the power consumption derived from those numbers. The software and EE teams that will be coming in will be doing hardware and software filtering in order to make sure that these components of our block diagram can work. That would be resistors, conductors, such. So the operating currents work with the parts. And now we're passing back to Austin to talk about our design approach.
Thanks, Marshall. All right, so really this graphic here really just shows the design iteration approach that we've taken since the beginning of this project. So at the beginning, we started by researching existing designs and researching existing projectiles out there. A few of those were like the Pike munition from Raytheon and others. And so we started looking at the advantages and disadvantages of different aerodynamic components, such as canards, boat tail design, straight body shape, different nose cones, to figure out how we were going to get our max range out of this projectile. So the top row is what our first preliminary designs were, and then from those aerodynamic calculations, those theoretical aerodynamic calculations, we then came to these three designs in the middle. We then realized that there's not a whole lot of publicly available data out there on projectiles because most of the applications are missile related. And so we came to the conclusion that we needed to do some wind tunnel testing for ourselves to be able to figure out which designs to go with. So these are the three designs that we went and wind tunnel tested, and these are our current designs that we decided to select after those wind tunnel tests. And to talk about the aerodynamics of our projectiles and our current designs and that iteration process is Corey Collins.
Thank you, Austin. So as Austin previously stated, that there was a lack of information that we were able to find. So based on that, we decided to do our own independent wind tunnel studies to help aid in some of our designs and to use as a tool for future iterations. We also wanted to just verify some of the initial calculations, specifically more with the lift and drag of the mortar shaped body, as well as looking for an optimal nose cone design. We did do 3 rounds of wind tunnel testing. The first round of wind tunnel testing was using a single body with the 3 nose cones, the elliptical, the OJI, and the long nose cone iterated through, and that was done at 82 feet per second. From that data, we did find that we were in the noise of the balance that we were using, so we increased the velocity to 148 feet per second using the mortar body design for the next 2 rounds. The reason why we did 148 feet per second for the wind tunnel testing is because that was the limitation, the max velocity that we were able to use for the wind tunnel. In reality, with our 1000 G acceleration, we're going to be exiting the barrel at 438 feet per second. So this is one of the data sets that we took using in the 3rd round of wind tunnel testing that we did. We did uncertainty intervals at 99.7% confidence levels, meaning that the data should be in between those error bars that you see there. As you can see, those data bars, the space in between them is quite large, meaning that the repeatability of the data was really not that repeatable. So the really main issues that we had with the wind tunnel testing was that our drag and our pitch moment coefficients, they were not well behaved. What we were able to determine was that since we're producing very little drag that we were actually reading 0.2 to 1.3% of the full scale value of the balance that we were using. An issue or a very large lesson learned that we went through this was during the wind tunnel test plan, we only accounted for the maximum loads that the balance could handle. We were far under those values, but we didn't take into consideration of being in the noise of the data. Given that after our wind tunnel testing, we did have to come up with a final design. And so the final component that we decided to choose for our final design for the body was the mortar shape. The nose cone, we went with the O-drive, and we have 2 competing tail fin configurations, a non-deployable 8-fin tail configuration, as well as a deployable system that sweeps aft as it exits the barrel. For our tail fin airfoil, we decided to go with a flat blade. The reason for the flat blade was because it's much easier to manufacture, to fabricate, and implement on the actual projectile itself. It's also going to reduce time in terms of manufacturing and tool work. We were looking for an airfoil that would be symmetrical. Anything else would induce a roll to our projectile, which we're hoping to avoid. So for our sizing for the tail fin, for our non-deployable tail fin, the image that you see right here on the parameter exposed is the actual tail fin configuration that we're using. It was difficult to do an analysis for it, so what we did is we superimposed each of the spans and made an equivalent tail surface, as you can see on your guys' right. With that, in order to get the correct area, we specified a static margin of 1 caliber, 40 millimeters, and with that, we're able to get a required time from error tail to ensure that we're going to be stable. With that, we have a static margin of 1.66 calibers. For our deployable tail fin sizing, the main issue here that we had was trying to make sure that we were stable as we exit the barrel. As you can see from our barrel configuration, the static margin is 0.15. We are cutting it close in terms of being marginally stable, but we still are stable. As we deploy our tail fins going into flight, our static margin greatly increases to 1.6 calibers. In terms of drag, we found that our deployable tail fin design would produce the least amount of drag, meaning that we're going to have a lot more range, which was our design goal. In terms of our percentage of our total CD knot value, our body was predictably a large percentage, and with the base drag and our tail fin drag to be interchangeable. These, the predictions will be confirmed when we start doing our flight testing. So here's our drag profile for our flights. In terms of our impact and our exit velocity, they're going to be very similar to around 438 feet per second. You can see from the range that our deployable tail fin system does give us the max range, which was predicted based on our drag values. which is around 30 feet larger than our non-deployable tail fins, with a rough flight of around 18 seconds. And now I'll hand it off to Walker to talk more about performance and stability.
Awesome, thanks, Gordon. All right, good afternoon, everyone. So again, I'm Walker Deem. I'm going to talk a little bit about the performance or predicted performance of our projectile underneath those aerodynamic conditions. So starting off with our calculations, I just want to lead with a list, pretty extensive assumptions that I made and that we made as a team about our performance and our performance characteristics and calculations. So the largest thing I want to hit on here is that in our range equations during the terminal phases of flight, it assumed that our drag was always greater than the y component of our weight. So that is a constantly decelerating projectile throughout its phases of flight. Additionally, we looked at little to no downwash derivative from the body onto the tail fins. Finally, the last two also I really want to hit on is a trimmed alpha of 0 degrees and a due to symmetry that some of your coefficients, stability coefficients, are actually equal. Additionally, one of the major assumptions that we have in this projectile is that due to the fins and non-spinning, that a statically stable projectile is also dynamically stable in flight. Additionally, we ignored some roll and pitch coupling effects on the control surfaces and the fins as they develop dynamic conditions. So going into some very initial time of flight and range estimates, we actually used 2 time of flight values and 3 range equations to independently verify our calculations based on each other and the aerodynamic conditions that we had. So as you can see, we're averaging at 1,000 Gs and 438 feet per second, an average flight time of about 19 seconds, and a range about 5,500 feet. Moving on to some of the stability parameters, I'd like to point out that in this slide, all lengths are expressed in calibers. So that means the ratio of, or the, correction, sorry please, the length of the projectile is expressed as a ratio of the diameter of the projectile. So if you took the overall length of the projectile and divided it by 40 millimeters, that is what you would receive, and that's the length. So 1 caliber is 40 millimeters. So the thing I really want to hit on in this is that both of our projectiles are longitudinally stable. Looking at our pitch coefficients and our static margins, we are going to cause pitch down tendency, and we're going to resist valleying in that aerodynamic condition. In the lateral directional, the same thing occurs. Something I want to hit is that value. That is a very large value for roll stability. It exceeds by quite a bit the standard conventions for aircraft, and that's what we designed off of. We designed most of our stability parameters off of aircraft stability parameters. I couldn't find a lot, even in the references that we were given, that differed the stability parameters from a projectile to the stability parameters in a rocket or mortar. Finally, moving on to the deployable, also, we are stable in the deployable configuration. The biggest difference I want to hit on is in the original design, our static margin was 1.66 in the 8-fin non-deployable. In this one, it is 1.6. So that slight difference in static margin means we are slightly less stable. However, anything over 1 caliber in stability in projectiles is higher than necessary, and 1 caliber is usually what you aim for. We went for a higher caliber or a higher static margin because if we have any errors or things like that in our calculations of our center of pressure or anything like that, that we can still have a little bit of safety room in terms of our CG movement and other factors like that. So finally, looking at this, we also have stable. We are stable in the lateral direction of the deployable tail fins as well. And just hit on again, here's a brief summary of both designs, their time of flight, range, and the lateral directional and longitudinal stability derivatives, parameters of each projectile. Now to pass it on to Troy Johnson to talk a little bit about mechanical packaging.
Thank you, Walker. So one of the main issues that we're going to have facing this projectile is interfacing our onboard recorder with the projectile. It's crucial that the onboard recorder does not have a lot of movement inside of the projectile so that our angular rates we're measuring are accurate. For this interface, the OBR will fit solely inside of the body. It will not extend into the nose cone at all. To interface the nose cone to the body, we're going to use a simple threading system. So we'll have male threads on the body, so the extrusion to the end of the OBR, and then female threads in the nose cone as shown in the figure to my left. To shift the center of gravity, to put the IMUs directly where we want it, to have the most accurate data, we can shave material from the inside of the nose cone or the inside of the body, or additionally we can also use ballast. Thread sizing and length of engagement for these threads are still to be determined, as this part of the design will be hammered out in our detailed design. Next, to cover because the bore of the launcher we're going to use is already provided and is 52 millimeters, and our projectile is only 40 millimeters, we're going to be using a sabot. Currently, our design for the sabot is consisted of 5 parts. We have a base plate and we have 4 fairings. They will be hinged at the base plate, as shown in the middle figure up to my left, and they will likely be spring-loaded. So as the projectile sits inside of the barrel, as shown at the top, it will be launched out of the projectile at 60 to 80 psi, from which the springs will cause the fairings to break away from the projectile, and then the projectile will continue in flight by itself. Material selection for the sabot is still to be determined, but currently we're looking into 3D printing with ABS plastic. Again, this is also a work in progress. The details will be finalized during our detailed design. Finally, the deployable surfaces. Because we have the challenge of increasing our aerodynamic data, we want to maximize our aspect ratio. Right now we're looking at hinging our tail fins at the rear that will fold forward. So then as the projectile comes out of the barrel and the fairings break away, the tail fins will follow that same exact trajectory as it breaks away and fold out upward. Right now we are also looking at a spring-loaded mechanism, though we are considering other options, and again, these details will be hammered out during our detailed design. And now to pass it over to Rachel for structural analysis.
So for the structural analysis, at the moment we have only looked at the launch conditions. So for this, the 5,000 pounds is applied longitudinally. That is due to the 1,000-pound G-force that we are, for my requirements, and the maximum of 5 pounds weight that we have. And the 1,000 pounds is a balloting load that is applied from the lateral 200G requirement and the same 5-pound requirement. For all the analysis that we did, we applied a factor of safety of 1.5, and from the material that we are currently looking at, which is 6061 T6 aluminum, there's an ultimate yield strength of 36 KSI and ultimate shear strength of 27 KSI. So first we analyzed shear along the body. We only looked at the 1,000-pound force that is applied laterally. We used a thickness of 0.12 inches, which is 3 millimeters. For doing the shear analysis, we did 8 equidistant points for the combined areas. And with that, we got a margin of safety of 2.6, as can be seen in the table. Buckling was also looked at for the tail section with only the 5,000 pounds being applied. This tail section was, we used a fixed free assumption where the tail is fixed to the body and the tail section is solid, and got a margin of safety of 2.73. So both of those are good as they are above 0. And analysis for the impact loads will be done early next semester, as we are still working on what those will be. And now to Daniel for finances.
Thank you, Rachel. So just a brief overview of where we're at financially right now. For the OBR, our projected cost with the components currently in the block diagram is about $330, which gives us a remaining budget for the OBR of about $4,100. For the projectile, our only cost incurred so far has been 3D printing costs of about $170, which gives us a remaining budget of about $2,300, which in total, cost to date, is about $507 with the projected OBR cost, and remaining budget is about $6,500. Obviously, these costs and budgets are subject to change as we finalize the design going forward, especially on the OBR side, when we're bringing another team to look at it as well. So, we also set up a labor hours tracking and set hypothetical costs to each of these 5 labor categories. So we set the rates to that, and we have a total of about 1,800 hours. That's actually about 100 hours larger now, as that last one was accounted for last week. Which gives us a total labor cost of about $142,000. This is our hours chart. We made a predicted hours estimate, and that can be seen in the dashed line, where our total hours can be seen in the solid line. You can see that we fall a little bit underneath the anticipated hours. This is due to things like we had to wait for 3D printed parts to be finished in order to wind tunnel test, things like that. There were a couple of roadblocks where we kind of had to wait for a couple of things to come in. Now, I'm going to pass it off to Will Smith to talk about the program risks.
Thanks, Daniel. So I want to start by saying that we've only started to look at risks that our program may incur. So this is a little bit preliminary, and it focuses mostly on the projectile side of things. So when we work with the EE team in the onboard recorder, we'll update this to account for some of those risks as well. So when we looked at risks of our program, we multiplied the probability of failure by the consequence of failure, and made a risk mitigation plan for all risks that were categorized above low risk. So this is a quick little summary of the risks that we looked at. The three that we developed a mitigation plan for were that high angles of attack would generate interference with the tail fins, that our predicted aero loading was incorrect, so that resulted in projectile instability, and then the last one was that the threads in the nose cone would seize or gall. So how did we mitigate those? For both the high angle of attack and the predicted aero loading, we've mitigated that by increasing our static margin. So increasing our static margin gives us additional room for that center of gravity to shift based on those loadings and will still be stable. To mitigate the thread seizing and galling, we're simply going to apply anti-seize to those threads, and that should reduce or eliminate that problem. Finally, I'd like to pass it back over to Conrad to talk a little bit about our conclusions and recommendations moving forward.
Thanks, Will. So just kind of recap what we talked about today. We talked a lot about our aerodynamic properties, our theoretical calculations, our basic performance parameters, proving that both our designs that we're iterating on right now are stable and are predicted to work. As Walker said, we have a huge assumption that a statically stable projectile will also be dynamically stable. So we have this assumption from references, and fingers crossed it'll work. But that is a huge assumption we have going forward. So one thing we still have to continue to design now is our sabo. That's going to be absolutely crucial to us being able to launch our projectile. As Will said before, when defining our system, we are going to be receiving this launcher from AxFab. It's 52 millimeters, which is 12-meter difference from our 40-millimeter projectile. So that's a pretty decent gap we're going to have to cover. So our sabo design is going to be absolutely crucial. That we will iterate more on. Our aerodynamic properties, we've talked a lot about wind tunnel testing, and that was a huge step for us to iterate on our design. As Corey mentioned, a lot of that data was not very reliable and not very accurate. So our aero team is going to be working with professors on campus to look into computational fluid dynamics, or CFD, so we can verify some of those calculations and continue to iterate to get to one design. And then we were expecting our projectile unit cost to be very low. As of right now, using 6061 T6 aluminum, we're looking around a cost of $26 per block to be able to machine that. And this will allow us to do some live fire testing, so we can take all those theoretical predictions of our performance, aero, and structural, and actually fire it and see what happens. So a couple of acknowledgements. We'd like to thank some professors who have given us a lot of insight. We've all learned a lot about aircraft, so working on projectiles like these is completely out of our scope, and we've needed a lot of help with this. So I just want to acknowledge the help from a couple of professors, and including Raytheon. The opportunity to go down and present with them was invaluable. So this concludes our preliminary design presentation. BYOBR, we believe we are ready to move forward to detail design so we can finalize our sabo and start getting a final design for our projectile. Thank you.
I'm gonna start at this end, we'll kind of work around this one. Sorry, I didn't. I'm sorry. All right, so go ahead, Doug.
All right, so I'm Doug Streeter, on projectiles. Brings back some awful memories. Okay, so you've got this Sabo you're going to put around your projectile. Do you have any idea how you're going to keep that thing in place before you launch? You thought about that at all? Is that next step?
Yeah, so right now we're considering using an operator ring on that rear plate, and then the springs, the tension in the springs will be just against the metal. But they'll be stiff enough to like retain and eject after launch, but they'll be loose enough to not cause it to get stuck.
And this is, so I don't know much about the launcher because I'm sorry I was late.
Yes, sir.
Can you give me a detail?
It's a smooth bore, there's no.
Smooth bore, okay.
So,
Just compressed air kind of
compressed
thing?
air, yeah.
All right. Okay, so bows are they're tricky, and that deployment thing, you're gonna have to look at that closely because you get some asymmetries when that thing pops open. It's gonna torque you around, and bad things are gonna happen. You probably want to put some aero features in that because your springs. It's good to get springs, but you might also want something that aerodynamically does make that thing peel away as well. Just things to think about. What makes your tail fins deploy on your deployable tails?
So it's the same, very similar. We actually were looking at integrating the tail fins and the Sabo into the same kind of mechanism. So not only having the Sabo come off with a set of springs, but use the tail fin springs as well as they spring back, torsional spring to push that Sabo out to kind of eliminate some of that asymmetry you were talking about. And then also the torsional spring
So
in the fins themselves.
So the tail's going to have a spring that makes it want to pop open.
Yes, sir.
Consider how, if it's not a very strong spring, you might want to consider a locking feature that keeps the fin open, just depending on if you get some disturbances in flight, so they can get more unstable. Your thread galling, I saw you brought that up. Aluminum on aluminum, it's awful, okay? It's really bad, okay? So, the NECs is good. You might want to look at maybe using a different material on one half of the joint if you can. But aluminum on aluminum is about as bad as you can make it. That they really do gall. And when they gall, it's done. You got to cut it off. So we'll look at that. The loads that you're using, those are provided by the launcher supplier.
Well,
Okay. Okay, so I saw you had validating loads in there. That's good. My experience is they're about 1/3 of whatever your what we call the setback load is. It's the kick in the butt that you're going to get. There's another load in there you might need to look at. It's called the set forward load. You push something out, you compress it, and now you come out. It's just you compress the spring and let go, so now everything goes into tension and wants to snap apart. So consider that so that you exit, you don't pop the nose off or something like that. So, let's see. Those are the big ones. So good job. Looks like fun. Thank you. Let's see how it goes. Very cool.
Yeah, Russ, you guys definitely want to do a great job. Really cool stuff you're doing. One of the things, so I see that you're designing for reasonable acceleration values for something that's 1,000 longitudinal, 200 lateral. One of the last things you said was we think we're ready to go build this thing. So one thing I didn't see really, the whole linchpin of this is that onboard recorder, and I didn't really see those loads applied to, whatever you're using. First of all, like component qualification or just a housing for it, it's sort of applied to the system you're structural analysis. Can you comment on that at all, or talk about that?
So next semester, once the OBR design begins, we'll have to write requirements based on the mechanical packaging of that. Right now, we've set aside a cylindrical area inside of the body for the mechanical packaging. It'll likely be some kind of threaded cylinder that's going to fit inside of that. So we'll have requirements based on stresses and applied loads onto that packaging. But that will be hammered out in our detailed design.
And to clarify, I don't know who came in when, but this is a 3-semester project. So this semester is generally projectile design. Next semester, we're going to bring on an E and SE team. They're going to work primarily on the onboard recorder. That's why a lot of those details haven't been hammered out yet. They'll continue, obviously, to the semester after.
Too early to think about what you're going to do to qualify that? Or is it going to be kind of like you put it in, you shoot it, and you see how it handles it? Or is there anything you can lab you're planning?
So I mean, based on our component selection from the, we can only see kind of like what the components we've selected, what they're rated for.
Yeah.
But as Daniel stated, we're waiting for the EE and SE team. We've kind of set forth the architecture for the OBR and where we'd like to fit in. But as far as like how the components are going to handle it, we haven't gotten to that yet.
I think what you're talking about is more design verification testing number one, and then qualification testing number two.
Yes.
And those plans can be done really early next semester.
Yeah.
So I think that's good.
I think this is the last thing I'll say. So you got bid by noise floor once already. So looking at some of your instrumentation specs, one of the things I saw was plus or minus 6,000 Gs kilometers. You might, so you're expecting 1,000 Gs at launch. I'm not sure how much you're expecting for impact, but everything in between, just, I mean, there's a lot of information here, I'm just kind of skimming over, but just make sure that you're looking at all phases of the flight, all the things that you want to collect, and making sure that you have an appropriate range. You might have already done that, but just keep that in mind that, you know, going overkill, you might put yourself in a noise floor for measuring, just kind of going along after the launch up to impact. So just something to keep in mind. But that's all I got. Great job, guys.
All right, going around then, Paul. Okay, now just one more question on the sabot. Is it designed to be reusable, or is this are the sabots going to be single-use sabots?
At this time, we have not finalized that detail. Currently, we're thinking about having it be reusable, but disposable is also an option because rapid prototyping is relative.
Okay. Now, and granted, I realize the onboard recorder, the majority of the work is going to be done, but you did lay out some of the requirements. Were they defined by the team here? Were they defined by you, Bill, or where the?
Yeah, so
I'm thinking specifically about the data frequency.
So in terms of the data frequency, we started looking at higher frequencies and higher durations, but that didn't necessarily meet off-the-shelf type components within our cost range. So that's something that we made a little bit of a trade on, and that we're still evaluating to see if we can increase both the frequency and duration and meet our cost target, or our target cost.
I suggest you talk with, early next semester, talk with the sponsor about that.
That was part of our discussion on Monday as well. And
Okay.
I think, Walker, you might want to chime in and articulate how you believe we're going to close in on that data rate.
Oh,
Do you recall?
so I do. So we still have to, from my point of view, look at our oscillation frequencies, so pitch and yaw and roll frequencies, to determine where our actual frequencies need to be for sampling, and then the Nyquist that we're going to come out off of that, so our Nyquist cutoff frequencies, and find our true true frequency we're required to sample at, and then kind of compare that with what we can afford and what we're going to trade off with, just so we're not sitting right on the edge, so we don't get any aliasing or anything like that, but still have good data.
Okay. Also, I'll caution you on your the 10G trigger for your initiation of your data collection. Speaking from hard experience, somebody walks by it and hits it with hits it with just a cable or something. You can get a very high frequency, very high G rate, and the system will act as if somebody hit it with a 10-pound sledgehammer. And so that's, like I said, hard experience. But I think Doug covered most of the stuff I wanted to talk about. Other than that,
A couple things, actually more than a couple things, but one thing you just mentioned was off-the-shelf components. Can you get electronic components that actually take 1,000 Gs? I'm curious because it's been a while since I worked on a projectile. It was a pain back then. I'm just curious now.
Yes, you can. There's a website that I've been using called Avnet.
Uh-huh.
They have a bunch of commercial off-the-shelf electrical parts.
Yeah.
And so that's where I found most of those components.
Okay, because, you know, the components themselves, I'm curious, it depends on what you mount them on, right? So that's going to be one of the critical things. What are you going to put these things on? I love the fact the way you guys put the risk evaluation, give you all the colors and everything. I haven't seen that. I've always seen, you know, give you the results right there, but here you gave us like a real quick, here's our risk evaluation. I love the summary of that one. On the calculations of the buckling, you know, I noticed you have a huge load. You did linear, right? It was just probably like an Euler equation or something?
Yeah.
Okay. The only thing I caution you on that is, and this even happened, like, I saw these guys do it. We were designing a torpedo, right? And they calculated the buckling load for it, but they used a linear buckling calculations. So the force was ridiculously high, right? But if you calculate the stress, you're way beyond yield, which means you are no longer in linear range. So just be careful when you do the calculation. Make sure you're not beyond the proportional limit, as in not the yield, but the proportional limit. That way it'll be valid. It's probably going to be okay, but just be careful with that. And also check the cylindrical section, because I think you checked the column section, right?
Yes.
Right, because when we did a projectile a long time ago, the head of the projectile, you know, the shell itself, we had to worry about the shell buckling on that too. Not only the tail or whatever you call the cylindrical part on the back end, that was, you just be careful with those. But also make sure you check the stress to make sure that, you know, your loads that you're going to get, you don't go beyond the proportional limit, because otherwise, totally invalid. And it's, you know, it was interesting that they got this far with the computer design before they realized it. And you're talking a corporation here. I like the fact that you identified that you had to use CFD on this because you just couldn't test it at that level. What would be neat though is you could now use this, you know, you said you use aircraft design equations, right?
Yes, sir.
So if you do CFD, now you could come up with your little, I don't want to call them flex factors, I call them correlation coefficients. So you can see what the differences are between them, right? Of course, my favorite correlation coefficient was always multiply by 0, and then you add the answer. But overall, good job.
Thank you. All right. Overall, yeah, good job, guys. And since I'm getting towards the end of the question line, pretty much all my questions have been answered. Comment about the sabot. Right now, it sounds like the sabot peels away, and then the fins kind of open up separately. You might want to consider somehow having a hook on the fins that attaches to the sabot, so that the sabot peeling away can help the fins open up. It's just something to keep in mind. It might make your analysis for the fin deployment a little bit easier. Another thing is, what's the max speed of this vehicle?
438 feet per second.
So
So that's going to be
still,
coming out of our
still in the incompressible regime.
Mach 0.37.
Okay.
Yes.
Good. Well, I brought that up because I was wondering if it goes faster, none of your none of your incompressible coefficients will work.
Yeah.
So just keep that in mind if you guys do decide to go faster. Still use the CFD. You know, I know you guys had a hard time finding actual data out there. CFD is pretty good nowadays, so use that as much as you can. Overall, good job.
Thank you. Thank you.
Okay, great. Yeah, I'm just going to echo the good job that everyone else is saying. It was really impressive to see some things, and we'll talk about a few things that I thought were especially good. One question, as far as the applying power at launch, is that, are you married to that? Do you have to go with that? The reason, one of the reasons that I'm asking, and forgive me, I'm not a projectile guy, but I wonder if there's initiation times. Especially, it looked like there was a GPS signal we were hoping to acquire, and you mentioned triaxial gyros. I don't know when you say gyro, I don't know if you actually mean like a gyroscopic thing that needs to spin up or anything like that. But
That's all an electrical component. Right now, the GNSS system is optional because of that fact, you know, so it's in the cannon, right? So when it comes out, it's gonna have time to track the satellite, and then once it hits, you know, that's our flight time is right now 20 seconds, and right now, our GNSS system is gonna pick up the satellite within 5 seconds, so it'll be able to track some of the flight, but it's mainly used to track where the projectile is after it lands, since at max range it'll be like a mile.
Okay, yeah, so I guess, and that's, you're hitting on a really important point. It's, you know, what are you gathering each of these parameters for? And as long as they're coming online, you know, whenever you need them, if it's just an end of flight to go find the item kind of thing, cool. But if you're trying to get any kind of launch conditions, then you might struggle. One thing to just think about, and then we'll move on, is whether power could also be manually activated. If there's some way to do that as an additional option, rather than just the G-load. Okay, enough on that. Slide 26, confidence levels on wind tunnel testing. How cool is that? I was really excited to see that. But I'm curious, what distribution did you use, or how did you decide that those were the confidence levels? How did you kind of, talk to me a little bit more about the statistics you did.
So we did, it was for the 99.7% confidence levels.
Right.
We did that just being that that's what we have been using.
Right, is that
from
assuming a
previous
normal
experience.
distribution, or what did you?
No, this was using the standard deviation.
Okay. Okay. Cool. Yeah, I think that all I'm getting at a little bit is think a little bit about the type of data that you're gathering and whether the assumption, because there are a million ways to lie with statistics. Think a little bit about the assumptions that the particular statistical method you're using is valid or not.
No, we made sure, because we took 3 data points at each angle attack.
Okay.
And so we made sure to account for the low number of sampling.
So great question, actually, and you're kind of hitting on the second side of it is repeatability. When you say you took 3 data points, did you do the test 3 times, or did you just hit record 3 times?
We hit record 3 times.
Okay.
Yes. And so we also, specifically for this shape, we did 2 rounds of testing. So these were done 2 different days, and the data was very similar.
Oh, okay, so actually you did 6 data points, if I hear you right. You did 3 and then 3.
Yes, just separate days.
Yeah. So that's actually, that really helps, because that's I think you're isolating different errors when you're doing it on multiple days versus recording three times on one day. That's great. I would highly recommend mentioning that somewhere as a note on your charts. Just to talk a little bit about methodology. It really builds confidence in the confidence notes. All right. Slide 36 and 37, awesome job citing sources for your assumptions, especially for a non-projectile guy. I tend to trust it, especially when you can cite sources about why you're allowed to assume certain things. Especially the top one there, the non-spinning projectile dynamic stability thing. Just a note, slide 39 and 40, it would have been good if you had units on numerical values. I think it's per degree, or maybe it's per radian, I don't know.
Per degrees.
Okay, yeah, again, just a note. Did you do plots of like CL alpha, CN alpha, that kind of thing?
Yeah, so we have all that stuff.
Okay, yeah, that would be something that I always love seeing the plots. One number, it's easy to fat finger the value, or otherwise have stuff that can be doubtful. So, hey, look. Okay, great. Yeah, thank you guys for showing that. And then slide 60, these are just a couple questions for the future. I'm curious, do you have any idea what range is going to be used for doing this testing? I know that's out in the long future.
So we're not doing it on campus.
Okay.
Thank you.
Good plan.
Right now, our plan is to talk to the police department in Chino and try to use their range.
Cool. All right. And then, do you have any, and this is again planned for the long future, think about plans to verify the accuracy of your instrumentation. Hypothetically, if there's a high-speed camera or something that can be used to watch the launch sequence, or some independent source of position, time information, those kinds of things are always amazing. I know it's hard, and you guys are working on a shoestring budget, so it's even harder, but try and think about if there are aspects of your instrumentation that you can verify and validate. As Bryce mentioned, lab is a spectacular place to try some of that stuff out. But this was just awesome. Thank you, guys.
Thank you.
Okay.
Before we leave, can I ask one question?
Yes, sure.
Vernon, do you mind if you stay behind? I have a lot of questions for projectile aerodynamics, and I'd love to get some help.
Sure, I'll stay behind and help you out.
Awesome, thank you.
I'm glad you asked that, because I didn't work in ERAU on projectiles, so Doug can attest to that. In fact, Doug would probably say I really didn't do any work on projectiles. But anyway, there were a lot of ERAU questions that I couldn't answer, and I got to applaud this team for being resourceful and trying to search as much of publicly available information as exists out there. And then when nothing turned up, they went out and decided to go build some wind tunnel models and go get some data on their own. So applaud to you guys. But I know that as this was going on, they wanted to know answers, and so I'm glad you're here. So thank you very much.
This is a valuable experience for you guys, because believe it or not, as engineers, working on projectiles, sometimes we don't have that data right away. So we go out and search for it on the internet sometimes and just see what publicly is available. So the fact that you guys have to do that, that's good skill.
There you go.
Now I know why Corey was asking you questions about OJAT configuration. Yeah, I know. Hey, this is great stuff, guys. I just have a couple things here. You said how these fins are against, and then they deploy this way. They open up this way. Yeah, with the Savo. Are any of you guys muzzle loader shooters? You got somebody that can do some research on Savos, because that's what they're shooting at. Now, I'm an old-fashioned guy. I wrap a patch around and press it down the barrel. There can use the Savos like that, and aerodynamically they feel off. So that's a good thing. And then you said one other thing, that you were unstable in roll.
So we are stable in all phases. The thing I wanted to highlight there is that value is pretty big. That roll stability value is pretty much 4 times what a standard aircraft roll stability value is.
Okay, I understood that you said it was unstable, which would give you spin, actually. So, okay, good. Thank you. Great job.
Thank you.
Thank you.
Good job, guys.